at an example, another example I should say, and we're going to say that we're going to look at a 1 horsepower motor. It draws 120 volts. It's drawing 16 amps at full load. And so we know that its impedance is 7.5 amps. I mean 7.5 ohms. And so that's our impedance, that's our Z. And we take a meter and we read the resistance of the windings, and we find that we have 5.25 DC ohms of resistance. Now, if that's the case, we've established a triangle already, right? So we have the side adjacent and we have the side hypotenuse, right? So what function do we have? We have the cosine, don't we? Okay, so we're going to go second function cosine, 5.25 divided by 7.5. And it says my angle is 45 degrees. That's a horrible, horrible phase angle, right? Cosine second function answer is 0.7. So this thing is 70% efficient. Now, 70% efficient, very good. That's not that bad. That's kind of average, normal, regular, cheap motor, right? Okay, now let's fix this thing. So at first we want to find our X sub L, right? We need to find our X sub L. What side is that? That's the side opposite. So we need the sine of this angle, right? And I'm going to go back into second function cosine 5.25 because I accidentally erased it. 7.5 as 45. Now I want to take the sine of that. So I just put in sine, second function, answer, enter. And I find the sine of this angle. And that's equal to what? O over H, right? O hell. And which of those do I know? I know my hypotenuse already, right? So we're going to say that this is equal to the side opposite, or the X sub L, divided by 7.5. Now to get O all by itself, we're going to multiply both sides by 7.5. Well, I've got 0.714 in my calculator. So I'm just going to multiply times 7.5. And it tells me that I've got 5.35607 on and on is my X sub L, right? Now if I want to know what capacitor to add to this, I want to take, this is the number of ohms of X sub L, right? And I want to take 95% of this, so times 0.95, and I get 5.08. So I know that I want to get rid of 5.0882 ohms, and that's 1 over 2 pi FC, right? So we're going to turn this into 1 over 377 times C. We're going to multiply both sides by 377. So I get 377 times 5.0882. And I get 1 over C, right? Well, 5.08 is still my calculator. So I multiply that times 377. And I know that's the reciprocal of my answer. So I'm just going to hit x to minus 1, enter. I get 0.000521. So what does that mean? 0.000. So that's 521 microfarads, right? Okay, now I don't think capacitors come in 521 microfarads. So let's round that a little bit to say 500. Is that okay? That might be too much rounding. So I'm going to hit clear, finally, and I'm going to put in 0.0005, 500 microfarads, right? Times 377. What is that? Isn't that 1 over C? 5.3 ohms. So we're going to have a new triangle, and we have right now, we have 5.356 ohms of X sub L. But now we're going to subtract. We just barely have enough to give. We're going to subtract 5.305. Just barely. We're going to wind up with almost nothing, right? Okay, well, let's put in 5.356 minus second function, last answer we got. And that's going to leave a piddly little 0.05 ohms, right? So let's put that in down here. So we're going to have an X sub L of 0.0509 ohms. And our new triangle has the same resistance. We can't get rid of our 5.25 ohms, can we? So we have a new triangle. And we know what? The X sub L, and we know the R. So that means we have a tangent, right? So second function tangent. And we're going to put in tangent, it's oh hell another of agony. So the opposite is the first number we're going to put in. So second function answer, enter. Not enter, second function, and then divide by 5.25. Close parentheses. And we get 0.55. What is that? That's our new angle, right? We're not even a whole degree. Well, let's leave this alone. 5529 degrees. Half a degree. That's pretty close, right? Okay, let's take the cosine of that. Cosine, second function answer. 0.99995. Pretty close. So it's going to take, what's 16 times 120? 1920? It's going to take we're still going to have that number of VAs coming in, right? But we're going to take that and multiply it times 0.9999. 1920. We've got 1919. 1919 watts. That's pretty efficient, right? We're only losing 1 watt to X sub L. That's pretty efficient. What was our power factor before? 70%. We went from 70% to almost 100%, right? 0.9999. If you round just the tiniest bit, that's 100% efficient, right? Close enough. Well, we're not going to use that 900 watts. We're only going to use, we only originally wanted 1 horsepower, 746 watts, right? So if we're only going to make 746 watts, we're going to draw a lot less current, right? To do the horsepower that we wanted before. Before, how much power were we drawing to crank out 1 horsepower? What's 2 times 746? 1492. 1492 is over twice as much power as you're cranking out, right? You're taking in more than twice as much power originally. But when we power factor correct it, now we're back down to 1 horsepower at 746 watts. So we're going to be cranking 746 divided by 120. It's what? 746 divided by 120. We're going to go down to 6 amps instead of 16. Originally, we were paying to draw 16 amps, right? Now we're going to draw 6. We're paying a lot less to do the same work. It's still a 1 horsepower motor, right? Yes, sir. Yeah, we'd actually be drawing in probably 747 VAs or somewhere around there, right? Because we're losing about 1 VA, right? So 747, I can live with that. All right.